It's my pleasure to introduce our second speaker, Professor Julia Greer. Professor Greer is Ruben and Donna Mettler Professor of Materials Science, Mechanics, and Medical Engineering at Caltech. She received a Bachelor of Science in Chemical Engineering at MIT and a Ph.D. in Materials Science at Stanford. Professor Greer, of course, has won many, many awards, among them the Kavli Early Career Award in Nanoscience, and she's recently been named a Vannevar-Bush Faculty Fellow by DoD, prestigious research award from the Department of Defense. Professor Greer is the director of Kavli Nanoscience Institute at Caltech. She's an associate editor of Nano Letters. I'd like you to please join me in welcoming her to the podium to tell us about materials design, by design, three-dimensional nano-architected metamaterials.
Well, a huge thanks to all of you, and a huge thanks to Chad for inviting me here, and to all of you for waking up early. Although, for inviting me to experience some sub 80-degree weather. Thank you for that. Now, so I have to follow a Nobel laureate's talk after a red-eye to Chicago. So bear with me here. All right, so I saw on these beautiful booklets that there's maps and methods and materials. And I promise you, I didn't participate in creating this brochure, but I am in fact going to show you some maps, certainly a lot about materials and some methods as well. So thank you for tailoring your brochure to my talk. All right, so the title of my talk is Materials by Design, so perhaps that part's pretty clear. And then there's the second part, and all of them are hyphenated, so chemically derived, three-dimensional nano-architectures. So that could be a mouthful, and I'm hoping that by the end of this talk, it becomes clear why they all belong in the same sentence. So I imagine you're all familiar with a situation like this. You go to the store and you buy all these things that you absolutely need, and the bags are just not quite strong enough to hold all the things that you need. So these are not the only examples. And so from the wine glass that never makes it to the toast, to the balloons that pop all too easily, to the I really meant to have 4 children situation. So these are all examples of materials that are lightweight, and because they're lightweight, they're very easily damageable and tearable. So in contrast, let's look at the materials we know to trust. So some of us are very intimately familiar with these. Of course, the airplanes are made out of very tough, strong materials. Well, the Boeing 747 weighs nearly 1 million pounds. And the tremendous expenditures in the airline industry come from having to propel a 1 million-pound machine through the air. So if we do a very back-of-the-envelope calculation, my ticket to get here should have been $30,000. So thank you very much for reimbursing me. Right, so of course the Dreamliner is already fixing these problems, and so these are by reducing the weight, these are examples of materials that are very strong and tough, and because of that, they're heavy and expensive. Now, another example of this, of course, is the solar panel installation. We have a lot of these in California, certainly a lot of these in Europe. And these are specialized materials, so if this guy or any of these objects slide off the roof, this is going to be bad news for everyone. So another example of materials that are too heavy by the virtue of their functionality. Speaking of materials that are too heavy, do you remember how in the last decade or so we've been discussing this idea of a space elevator? Well, as far as I know, there still isn't one. And the reason for all these problems is actually this very densely populated map. So I chose to show you some mechanical attribute here. It can be strength, as it could be toughness, it could be stiffness. I chose strength, but it could be any other mechanical attribute. It's a function of density. And what you see here are these colorful domains, and they represent all the materials we know how to make today. And the picture that emerges right away is that we're very good at making materials that are simultaneously strong and heavy, or simultaneously lightweight and weak. What we're not so good at is hitting the so-called white space, and that is making materials that are simultaneously lightweight, but also are mechanically resilient. Now, I put the theoretical maximum here. Certainly we can't go above the strength of a chemical bond, but this is a log space. So even a small increment within the space already represents a substantial change. So how do we do this? How do we hit this white target region if everything we know how to make today is already plotted here? So the way we do it is by introducing the concept of architecture into material design. So if you look at the Great Pyramid of Giza, this is the largest man-made monument. So it stands 150 meters tall and it weighs nearly 6 million tons. Now, in contrast to the Eiffel Tower, which stands twice as tall, and it uses 3 orders of magnitude less materials, so 1,000 times less. So, utilizing this concept of architecture into material design, we began this work maybe 5 or so, maybe 6 years ago now, with the microlattice. So what you're looking at here is an microlattice that's made entirely of nickel. This is work in collaboration with HRL, and it's sitting on the world's most normal dandelion. There's nothing photoshopped here. This is not the world's strongest dandelion. It's sitting on top of the world's most normal dandelion and hardly perturbing it at all. So it's exceptionally lightweight. In fact, if I were to hold one of these in one hand and a feather in the other, and then to release them at the same time, the feather would fall down faster. These are very, very lightweight. Now, what we're after is not just the lightweight, but the simultaneous attainment of the lightweight and the strength. And for that, you have to go down to the nanoscale. So what you're looking at here are all these examples are of the different nano architectures that are made in our group. And so you can see, perhaps those of you who are fans of Doctor Who, here's a nano TARDIS. So this one is about 1/10,000th of your hair diameter. It's micro TARDIS, actually. And the rest of them are relatively periodic, or at least somewhat regularly patterned, 3-dimensional architectures. There's an obvious level of porosity that you are observing, which is what gives them the lightweight, which is the fact that they're all cellular solids, so they're very open, porous structures. The slightly less obvious layer of porosity here is this. The tubes that comprise these 3-dimensional interwoven networks are hollow. And the wall thickness of these tubes can be anywhere between 5 nanometers up to hundreds of nanometers. So the largest dimension in these solids, anywhere you probe, is just that wall thickness, which could be 5 nanometers. So when you look at these materials and they sit on your hand, they look like a solid cloud or like an aerogel. But when you actually zoom in and try to measure anything within them, you realize very quickly that they're 99.9% air because of this. So this is what gives them the lightweight, but what we're after is the combination of the lightweight and strength, and so this is where the nano size effect comes in, very important. So at the nanoscale, all the common materials exhibit a so-called size effect, which turns out to be very pronounced and very useful. If you look at a variety of common metals, what I'm showing you here are metals like gold and silver and copper and nickel in their single crystalline form, so no grain boundaries. And what you're seeing is that the strength becomes tremendously higher. There's a tremendous amount of strengthening in a power law fashion as you reduce the dimensions. What that means is that if you look at copper or take a gold earring, we know them to be very malleable, and you reduce their dimensions to about 200 nanometers or so, the gold becomes as strong as steel. So smaller in this case is stronger. Now, take exactly the same metals and deposit them using different techniques. For example, sputtering or PECVD or all the nano deposition techniques that you are all familiar with. And all of a sudden, this effect is reversed. And now, smaller becomes weaker. This is a more modest size effect. It's not an log-log plot, but nevertheless, the smaller dimensions now give rise to weaker type materials. So now you're starting to think, oh, it's the same metals. But now we have this tunability in strength by the virtue of size reduction in a different atomic level microstructure. Now, the size effect is even more powerful than that. If you look at a glass, so this is a glass rod. It's about 150 nanometers in diameter, and we're going to pull at it. Now, of course, we all know that's not possible. Nobody at room temperature. Nobody's able to just pull on a glass rod and get anything useful out of this. So if you look at the stress strain data that we're collecting simultaneously, and especially if you focus on this region, you will see the formation of a neck prior to failure and an extendability of about 100%. So at the nanoscale, it turns out at the room temperature, you can actually pull on a glass rod and it thinks that it's behaving like a metal. Here's the last example. If you look at a ceramic nano architecture, this is just a single unit cell. So this is made out of titanium nitride, very, very brittle ceramic, and we're pushing on just a single unit cell. What you see is that these beams are deflecting, and they're deflecting so much so that the tensile stresses that are generated here exceed 1.5, 1.7 GPa. No ceramic should stay intact at 1.7 GPa of tensile stress. But this guy, not only is he staying intact, but he's doing this over multiple cycles. So the takeaway message here is this: sometimes materials get stronger, sometimes they get weaker, sometimes you can suppress brittle failure, but all of these effects emerge only at the nanoscale. And so the question is, can we somehow harness these beneficial nano-size-induced phenomena and proliferate them onto the larger scales? And that's where the three-dimensional nano-architecting comes into play. So just a few words on how we create these very intricate geometries. Instead of using UV single photon lithography, which is a very typical process for two-dimensional lithography, two-dimensional architectures, we're using a process called a two-photon lithography. And that allows us to concentrate all the light and all the exposure within the photosensitive resin in a single voxel. So it's the constructive interference of exactly two photons that gives rise to the sufficient amount of power to cross-link your polymer. Now, as this voxel is rastered in three-dimensional space within the resin, it creates a pattern that we desire. There's no mask required. We're not limited to periodicity. I can write a nano version of each one of you, so nano chat is going to have a different meaning after we do this process. So we can create, I guess it's chat nano, sorry. So we create whatever scaffold we desire without using a mask. And then what we end up with is this scaffold, but that's made out entirely or cross-linked acrylic resin. By the end of this talk, you'll see that that's not the case, but that's what most people do that use this technique. Now, we're not going to go build airplanes or anything useful out of these. So what we do after that is we often coat these scaffolds with the material we actually are interested in. Now, how many of you are familiar with ALD, atomic layer deposition? Quite a few. So in the ALD community, they say, we can deposit anything you want for you as long as it's alumina. So here's some alumina. This is an example of depositing alumina. It doesn't have to be aluminum. We certainly have used many other techniques, but this is how we started. And then the form factors in which we typically use make our samples are typically cubes, and so that allows us to expose 2 out of the 6 faces and then to etch out the scaffold that was so painstakingly written. So in the end, we end up with these hollow replicas of what we had originally designed, where the only dimension of a solid is that wall thickness of the ALD deposited alumina, for example. So here's a movie in real time that shows you, is there a nanoscribe here in the IIN? Do you have an instrument that has this? So maybe some of you are familiar with this instrument. So this is what it looks like in real time, this two-photon lithography process. You can see resolving the architecture. It's not very slow, but it's also not very fast. So you can think of you can think of this in real time. Now, everything we make is pretty small, so you can't really resolve the features just by optical microscopy. So we built a special instrument that allows us to really perturb these structures and to study their behavior. So without all the whistles and bells, this would be just an SEM chamber. Of course, everyone's familiar with that. We also have the capability to do electrochemical measurements, and I'll share with you some of the results in that realm. Also a nanomechanical module. We're very nanomechanically oriented lab. And then also a cryogenic module, which allows us to span the range of temperatures and study deformation at different temperatures. And these are the different inquisition devices. So we can pull on them, we can push on them. You can see that the opening here is roughly 200 nanometers. So we can pull on very, very thin, very individual freestanding nanostructures, as well as push or pull on much larger structures that are several microns. So several hundreds of microns. So here's, so this was our hypothesis. Can we proliferate the size effect, right? So about 5 years ago, we did this experiment where we tried to probe this hypothesis. So we made a hollow octet truss. So this architecture is a hollow octet truss. The wall thickness here is 50 nanometers, so it's very, very thin. It's very porous, and it's made out entirely of ALD alumina, so very brittle material, right? So imagine your coffee mug with a severe case of osteoporosis. And we're going to push on it, so of course it's very brittle, very breakable, so what do you think will happen? That's not a rhetorical question. What do you think will happen? It'll die, right? It'll crash and die, so let's see if that's what happens. So we're loading it elastically, just like we would expect, and then it crushes and dies, just like we expected. It's not even trying to recover. We have a little nanocemetery in our tool, and it's pretty much dead. There's only one good thing, and this is actually kind of important. If you look at the stress strain plot here, you can see that its strength exceeds 25 MPa. Something that's 99.9% error shouldn't have anything be measured in mega units. Shouldn't be mega anything. You could be kilo, pascals or pascals, but this is 25 MPa, so it remains strong. Now, all right, well, so, it remained strong, but it didn't do anything else interesting. So we repeat this experiment, and we repeat this experiment in the following way. We keep everything the same geometry, the same material, the same microstructure. The only thing that's different now is we're reducing the wall thickness by a factor of 5. So now instead of 50 nanometer walls, we're going to have 10 nanometer walls. Same alumina, very, very brittle, even more brittle now, right? So we're going to compress it. We should experience the same behavior. And so here we are. So this is my former student, Lucas Meza, is compressing this, and he's compressing it almost to 50%, and we're waiting for it to crush and to die and to fracture in every way. And this particular ceramic thinks it's a sponge. So if that doesn't convince you that there is in fact a size effect, I should just turn around and fly back to California right now. So the only difference is the wall thickness, but the deformation behavior is drastically different. So this is not the only example. We have since uncovered many more different realms of this behavior. What you're looking at is this is a periodic hollow alumina nanostructure. This is a nano labyrinthine, we call them, or bicontinuous surface nano-architecture. And you can see that they both recover and store and absorb energy exceptionally well over multiple cycles. So complex architectures, complex stress states, not periodic. You can see that the density doesn't have to be homogeneous. And what I'm showing you here is a material that has two different density regimes. So this is, of course, lower density, higher density. And at this point of compression, this part of the sample doesn't even know that it's being compressed. So you can pre-build trajectories of deformation and trajectories of how the stress and the strain is going to respond at different strain rates. So that gives you that flexibility. Now, this particular nano architecture is fractal. So you can see that each individual beam is now comprised of self-similar unit cells. And as we're all hollow, and as we're compressing it, you can see that it's kinking. It kind of hurts me every time I watch this video. You expect it to snap at any point now here, and it fully recovers. So you can see that this effect is ubiquitous over complex architectures and complex stress states. So what's going on here? How do we explain this? Well, turns out the answer lies in mechanics, as we often find out, as our mechanics community likes to say. So these architectures are mainly comprised of beams, and not just beams, but hollow beams. And the phenomenon that would allow recovery after deformation in a hollow beam would be through elastic shell buckling. So think of your soda can effectively, right? So, all right, well, we can come up with a criterion then for buckling. So if you look at an individual beam whose radius, for example, is A and the wall thickness is T, there's a ratio. There's a T over A ratio, basically how thin-walled is this cylinder, which is comparable, or can be compared to the fracture strength of your material, so failure strength when this alumina would fracture. And turns out that for this particular material, the critical ratio is 0.03. So what that means is that for geometries that are below this ratio, that we should be able to observe the shell buckling. For the geometries where it's higher than that, it would fracture before. So let's see if that's what happens. So, whoops. So for the 10 nanometer wall thickness, that's the image, that's the sample that you saw recover, you can see that no matter what the unit cell size is, every time it recovers, this is an image of one of these samples after the deformation, which you would never be able to tell the difference because it looks the same. And of course, this seems to be checking out. So now, as we increase the wall thickness, you can see the deformation is becoming much more jerky, much more drastic, much more discrete. And then this last one doesn't even try to recover at all. So it turns out that the answer lies in mechanics. So what that means, so T over A is scale-free, right? And so what that means is that if we were to build a building that's comprised of giant concrete tubes whose wall thickness is 10 centimeters and whose radius is 3 meters, and the whole thing is 3 kilometers by 3 kilometers by 3 kilometers, I'm sure there's a building like this in Singapore somewhere, and a big giant comes and steps on it, it'll snap right back, just like our Nano Letters did, right? Okay, I hope that was a sarcastic right. Thank you for that. Of course not, this would never happen. But why not? Mechanics tells us that it should. So how does the size effect, the nano size effect, manifest itself here if the the mechanics is right? So T over A is scale free. As long as the T over A is below 0.03, it should work. But this would never happen in a building like that. You're all absolutely right. Why not? Also not a rhetorical question. Any ideas? Those of you who know, please don't say anything. So it turns out that the answer lies in defects. The probability of finding a flaw in something that's 10 centimeters thick is 100%. Not just one flaw, but millions of flaws. Any little micro-inclusion, any little void, any little pore. And then the local stresses at those defects will far exceed the globally applied stress. And so, of course, the material will always fracture before your structures ever get a chance to shell buckle. So this would never happen with such large dimensions because of our ability to make much more perfect materials when their dimensions are reduced to the nanoscale. So the size effect manifests itself here is in our ability to make much higher quality materials. If we were to make an architecture that would fill up this entire room where the wall thickness is only 10 nanometers, that would be a much higher quality material than if we were to occupy the same volume with a bulk material of the same chemical composition. So that's the nano size effect, right? So the right answer is no. All right, so now at this point, our questions were originally, did we hit the white space and how close can we get to theory? So just to remind you, this was the parameter space before, and then these are all of our points that we've accumulated over the last few years and just on the hollow alumina. And you can see, for example, is that we already bought ourselves a 2 orders of magnitude reduction in relative density in the white space where people hadn't really been before, and perhaps some of you can do even better than that now. We can do better than that now. So this was sort of the first venturing out into the white space. Now we can do much better than this. So here's an example of carbon that we just published this work very recently. You can see that at higher densities, the carbon actually does in fact approach theoretical limit. We also kind of had to revisit this theoretical limit. What exactly is theoretical limit when you're talking about materials that are practically all surface? And those of you who work on 2D materials certainly know that effect very well. Right, so we are now at a point where we can create entirely new classes of materials with unique, unprecedented properties. So that gave us a rush of many more questions. So what is the effect of architecture on the mechanical performance? What's the role of defects? How do they behave under tensile loading and under fracture experiments? Can we optimize them? And then I put down second and third harmonics of these questions. Of course, there are many more the questions themselves are hierarchical that are building upon this. But this is the time in the talk where we take a dramatic pause because I can't tell you about all of these things. So everyone takes a big breath. And I'm going to tell you about one of these things, and you get to vote. So I can either tell you a lot more about mechanics, I can tell you about biological materials like bone, I can tell you about fracture, I can tell you about mechanics and batteries, and many more, and dynamic loading, so shooting things, bullet-like projectiles onto these. Or I can tell you a lot more about chemistry and about additive manufacturing and about how we don't have to be slaves to the photoresist that you would buy from Nanoscribe, and how you can actually additively manufacture many exotic materials and many non-exotic materials with very small dimensions. So please take a look at these two. How much more time do I have? 20 more minutes, possibly? Yeah? Great. Awesome. All right, so I will tell you only one of these stories, and I'd like you to take a look and to take a vote. So everyone has to vote once and only once, and you can't abstain. All right, so who wants to hear more about mechanics? Wow, both of you. Okay, great. Who wants to hear about additive manufacturing? Okay, a lot more. All right, so I'll tell you the story about additive manufacturing, and if anyone would like to talk about mechanics later, I'll be around for the whole day. All right, can you help me click basically on that little orange square, a rectangle? Can you just click on it, please? No. Yeah, if you just click right on that. No, on the orange. No, on the orange square. Yeah, nope, square. A rectangle. The rectangle, it's a geometrical shape. Right, okay. Can you just put it on the orange rectangle? Right here. This is an orange border, anywhere on this orange border, and just click. Yeah, click. Thank you. All right. Okay, thank you. All right, so we did not want to only practice our two-photon lithography 3D sculpting using IP-dip and IPS, which are the two commercially available resists. And so last year, a couple of years ago, my student looked at these resists and he said, well, I want to try to make something else. In fact, I'm very interested in additive manufacturing of metals. So this is where we begin our additive manufacturing story. He looked into a ligand exchange reaction. And what we mean by that is that if you have a metal ion that is trapped inside of an organic shell, you can actually mix it with acrylic acid and then interchange it for the acrylate groups, which then become amenable to photoinitiatable type of reactions. So when we mix these organic and inorganic parts, so the acrylic resin for cross-linking, and then this nickel acrylate, and then as well as a photoinitiator, this creates a resin that could be amenable to light. And so at the time, we didn't know if it was going to work, and we got extremely lucky because it did. So what you see is that this is the nickel-containing resin. So look at the unit cell size here. It's about 10 microns. And the beams here are roughly 2 microns or so. So this is an organic, metallo-organic compound. Now, how do we get rid of the organics if what we're really interested in is nickel? Well, you burn them. So what we did is we pyrolyzed this structure, which is a fancy word for burning without oxygen. And when that happened, of course, a lot of the organic material volatilized, all of it did, and the concomitant shrinkage that came with this ended up allowing us to have the resolution of the final additively manufactured structures to be only 2 microns in terms of the unit cell size, but each individual beam here is about 400 nanometers. So my student Andre made these, and then the question, of course, was, well, all right, how nickel is this nickel? You say it's nickel, but is it really nickel? It's all chemically derived, it's new. So here's the as-printed resin, here's the resin after the pyrolysis, and what we're learning is that there's actually quite a bit of nickel. So this is the EDS spectrum, of course, that shows you that quite a bit of nickel, maybe a little bit of oxygen, but that's not really how we tell the chemical composition or the microstructure of materials. The way we do it in material science is we do TEM, transmission electron microscopy, that allows us to look at the atomic level composition. Now, how many of you have used TEM before? So you know how challenging it is to prepare these samples, right? How do you convince an additively manufactured 400 nanometer beam to jump onto your TEM grid? It's not easy. So Andre was particularly ambitious and he said, well, I'm going to write a grid on top of a TEM grid, and I'm going to pyrolyze, and I'm just going to hope that one of these beams is going to subtend one of the holes. And sure enough, we got very lucky. So this particular pyrolyzed beam is, in fact, located over one of these holy membrane holes, and that's when we say, hallelujah, we do this every day. It's no big deal, works every time. Yeah, so what's really nice about this is that this particular sample has never seen the fib, has never seen any damaging ion effects. It's as manufactured material. So everything we see is a result of this process. And what we're learning right away is that, first of all, is that it's nanocrystalline. So the mean grain size here is about 20 nanometers, so 20 nanometer grained nanocrystalline nickel. We see that's mostly nickel, so you can see this very clear diffraction pattern. We see a little bit of nickel carbide, and we also see some nickel oxide, which very likely formed after just on the surface as a result of native oxide formation. Now, let's think about this. It's nanocrystalline and it's nanoporous. So it's terrible for the mechanical properties. You don't want to have your metal be nanocrystalline because then it becomes brittle, and you certainly don't want it to be nanoporous because those are all defects, right? So its strength should be terrible. So we're pretty good at measuring mechanical properties, so that's what we decided to do. So here's our nano-architected nickel, entirely made out of nickel, nanoporous, additively manufactured. And so we're compressing it and we're looking at the strength. The porosity here is about 30%, so it's not super lightweight, but it's still nanoporous. So we're looking at the stresses here. Well, they're about 15 MPa, and then once we've fully densified it, of course, it shoots up. So it deforms just like we would expect it to deform. So to place it in the context of other additively manufactured materials, we created this plot. So what we're showing you here is the specific strength. And so what that means is that it's strength normalized by density for a variety of other metals that were created using other additive manufacturing techniques as a function of the beam size. And we were very surprised to learn this. We were delighted actually to learn this. But the additive manufacturing techniques that exist today seem to not deal so well with the size reduction. When their dimensions are about a millimeter, so this is 1,000 microns, right? So a millimeter, they're doing great. Their specific strength is very high. This is silver and titanium and nickel, nitinol actually, in fact. But as soon as you start reducing the dimensions from 1 millimeter even down to 100 microns, it loses strength very rapidly by 2 orders of magnitude. Additive manufacturing techniques that exist today are not robust against defects. Now, when we plot our materials here, which are terrible, by any conventional measures, the microstructure of the material is terrible. Here's what we're observing. We're observing that we're 2 orders of magnitude below what the best additive manufacturing techniques can do today, but their strength is comparable to something that's about 500 microns. And in fact, we had to put a huge break in here because if we were to follow the trend, we would be expected to be here, so 7 orders of magnitude below. This is not a fair comparison, but just to show you how much higher the strength is. So what this tells us is that at the nanoscale, not only do you gain strength benefits, but your materials become much more forgiving to defects. And so the combination of this leniency against the defects, as well as the size effect, propels the strength of these nano-architected nickel materials and other metals to be quite respectable and very much comparable to something that is currently possible only at roughly 1 millimeter or half of that dimension. So we were pretty pleased with this work. So of course, Andre, this is the student who made these, wasn't just going to stop at nickel. And he said, well, okay, if I can make nickel, maybe I can make other metals and maybe I can make other materials. So his interests shifted towards multifunctional materials. So he went after titania. Using this same ligand exchange process, he went after creating titanium dioxide. Now, titanium dioxide has a variety of interesting properties, one of which being is that it's photocatalytic. And so what that means is that when you expose it to sunlight, it creates free radicals, which then can go and kill some microorganisms like E. coli, for example. So here's an example of nanoscience actually being a methodology where it's being applied to solve a useful problem. So he created these these are not nano-architectures, these are micro-architectures, because they can serve as water purifying devices. For example, you can insert one of these, I'm not sure if you can see it, but here's a nanolattice or microlattice inserted into a solution of methylene blue, which is kind of like an E. coli type microorganism. And you can see that with time, it deactivates it. So this blue color turns into clear with the presence of this titania lattice. So you can imagine inserting these into water bottles, which are full of E. coli or other harmful bacteria, exposing it to sunlight, and voila, you have your water purified. And the advantage here is that the titania scaffold is not in the form factor of nanoparticles, which you can't extract out of the water. This you can just lift out of your bottle, and so you don't have to drink the titania as well. So here's one example. Now, titania also has nanophotonic properties. So when you reduce the dimensions of these titania nanoarchitectures, again, here's the very bulky molecule, monomer that ends up here. And then once you use 2-photon lithography to create these at the smaller scale, so you can see now the resolution here is only 1.5 microns. So we're reducing it back down to the nanoscale. You can see that the emergence of, now you can see the emergence of a photonic band gap, and you can see in the IR, and you can see that this band gap is shifting as a function of the periodicity of these structures. So titanium, of course, is a high index material, so you can do quite a bit in the realm of nanophotonics using these additively manufactured materials. And also, we were delighted to finally perfect the shape integrity. This took some time, but you can see that these beams, the titanium beams, look, their shape integrity is much better than when we first started with nickel. So there's certainly many ways to improve these types of devices. Now, the metals and the metal oxides using ligand exchange reaction are interesting, but they're still acrylate based. So if you wanted to go to a different type of chemistry, for example, more benign, more green chemistry, it would be great to shift our efforts towards hydrogels and towards aqueous type, or rather towards aqueous type syntheses, so where we don't have to use the acrylate based chemistries. And so here, this is the work of my student Daryl, who took a bold step actually in the direction of hydrogels. So now what Daryl noticed is that if you take a metal salt, and here in this particular example, he's using zinc nitrate. So you can use this metal salt based synthesis to do swell-in type of reaction, and then cross-linking and trapping the metal ions inside of this hydrogel network. And then it's no longer called pyrolysis. So when you burn things with oxygen, it's called calcination. I'm learning all sorts of chemical things here. So when you calcinate this in air, what we end up with in this particular case is a zinc oxide architecture using aqueous only synthesis, no acrylates here. So again, trying to understand the nature and the chemical composition of these zinc oxide structures. So it looks like we did in fact make zinc oxide using this hydrogel-based synthesis. This was an entirely new adventure. We didn't know if this was going to work. Sure enough, it did. And what we're learning also here is that it's very nanocrystalline, even more nanocrystalline than the nickel. In fact, the mean grain size here is only 5 nanometers. So what is the one property of zinc oxide that all material scientists know about? I'm having a hard time hearing. Can you talk louder? Piezoelectric. That's right. Thank you, whoever just said that. So, thank you. So it's piezoelectric, right? So we made these zinc oxide nano architectures. So now it's time to check if they're piezoelectric, but they're nanocrystalline. But if they're nanocrystalline, all of the dipoles are going to cancel each other out. We're never going to see that response, right? Because piezoelectricity emerges as a function of dipole separation in single crystals. Right, so let's see what happens. Well, all right, so look at the first top part here. So this is the resin, the zinc oxide containing resin. Of course, it shouldn't have a piezoelectric response. Now, in our instrument, I showed you that we have the capability to assess the electrical response of materials in addition to the mechanical. So that lends itself very well to piezoelectric type experiments. So what you see here is the blue signal is the voltage, and the orange signal here is the displacement. So what we're doing is we're coming in contact with the structure, and then we displace it by something like 350 nanometers here in a step function. And what happens to the voltage? Absolutely nothing. No response from the resin, as we would expect. Now, when we burn off the resin and we convert this fully to zinc oxide, right here, we're doing exactly the same experiment. We're pushing on it, maybe only 200 nanometers, and we very clearly are observing something like a 20 millivolt change in voltage. So it's working. Why does piezoelectricity work in nanocrystalline material? What's going on? The reviewers asked us the same question. We managed to publish, so we actually now know the answer. But it's weird, right? It's surprising. We shouldn't be observing it. You look at the grain structure here. First of all, the grains light up in all multiple orientations, so they're very randomly oriented out of plane. But we're still observing the signal. Turns out, it's actually not that interesting, but this amount of voltage drop is very small. We should actually get a much larger drop. And in fact, if we had a single crystal whose C-axis was oriented along the compression axis, we would have gotten an even greater response. It's simply the fraction of the grains whose C-axis happen to be pointing in that direction. And so when you take that fraction, just the rule of mixtures, and compress it along those directions, that's the response you see. You just see the response of those grains whose C-axis are in fact favorably oriented. So we're getting the piezoelectricity from the individual grains, and because our structures are so small, we're able to detect them. So this was an exciting endeavor. Now, we decided to go backwards. At this point, Daryl said, well, I can make metal oxides using this hydrogel-based synthesis, so can I reduce them now to go back to the metals to make other metals not using the ligand exchange reaction? And so this is Daryl playing with nickel and with copper. You can probably tell which one is which, right? So this is the swollen, the hydrogel, with the copper ions here and the nickel ions here. You can see the characteristic color. Then we calcine them, burn them, so they become black. So these are the oxides, and then after that we're able to reduce them by placing them in the reducing environment, and you can see the color that emerges as shiny copper. So this is pure copper, and this is pure nickel. Now, these are all additively manufactured metals using entirely chemical-based synthesis. So these are chemically derived materials, and we're entering a new era where all of the additively manufactured materials are now becoming chemically derived. And so we need to really start opening up this space and start understanding our materials from that point of view, that their nature no longer comes from some ore in processing and the triangle, the material science triangle, you know, processing structure properties, but entirely from chemistry. Now, I think that this person is trying to tell me that it's my time to finish things up. So we also work with Nobel laureates at Caltech quite a bit. So this was our paper with Bob Grubbs, the first paper with Bob Grubbs that shows that you can also functionalize the surfaces of these structures, for example, with DNA, and then DNA can bind onto various chemotherapy agents, for example, like doxorubicin, so you can capture various chemical functionalities and make membranes out of them. Very recently, we started playing with shape memory polymers, so you could start building different chains and program your structures using the glass transition method, for example. And so what I'm showing, this is the work of my student, Luizetta. This is all new work that shows you that you can program the cycle. You can program them at hot temperatures and then lock the shape, and then reduce the temperature, and it'll retain that shape like the flower is doing here. And only when you increase the temperature back up and heat them back up will they go back to their original shape. So you can imagine shape memory effect being used in stents or in very, very small, these are very tiny architecture, so you can imagine using them in the eye, for example, or somewhere where the vessels are very small. Just a few words on making lithium cobalt oxides. So this is very relevant for battery materials. So looking towards all solid state batteries, we can now use these synthesis routes to produce lithium cobalt oxide in different shapes. And I think I want to finish with this little story. Can I possibly have 2 more minutes? 1 more minute. Oh, yes, I can. 2 more minutes. Great. Okay, so I, as a human being, I'm actually very interested in defects. Like I just really like defects and studying defects and the effect of defects on various material phenomena. So I mentioned this battery, the lithium cobalt oxide. So I have a few students who are interested in batteries, and this is one of them. So he decided to make a battery out of these. So this is a tetragonal microarchitecture. And you can see that there are beams basically subtended over these unit cells of tetragonally shaped lattice. And the idea being is that once you lithiate it, they will buckle out of plane. And so here's one of these. This is a top view of one of these lattices as they're being lithiated. Yeah, as they're being lithiated, and you can see what ends up happening is that these are these sinusoidal type patterns that evolve. Actually, they look like violin. I'm a musician, so to me they look like violins. So you can see these sinusoidal patterns that are developing in response to lithiation. And so this is a good situation because instead of cracking, which is what we would expect for silicon, what we're observing is that these beams are bending out of plane. And so this is a true battery, just to show you, this is not just pretty pictures and videos, it is in fact a battery. So for the 0.6 volt cutoff voltage, we can see that here's the specific capacity. It's doing a pretty decent job. It's not the world's best battery. It's an okay battery, but it is a battery nevertheless. So looking at these electrochemical properties, we realize that actually changing the rate at which we lithiate them gives rise to different domain formations. And so these are all SEM images. These are not computer simulated. These are actual SEM images of some of the different patterns that form. Well, why do these patterns form? Well, it turns out it's all about the defects. And actually, we can use this antiferromagnetic type icing model to describe the coupling of these domain formations within these networks. And so we were able to simulate, to put the theoretical framework over this. So these are the simulated patterns. These are the real images and simulated patterns. And it looks like there is, in fact, quite a bit of coupling going on between the randomly distributed defects in the structures and the defects that we can program in. And so what we learned is that if you start with a silicon lattice and then you lithiate it, you form this intermetallic compound, and then you're forming this compound, your band gap, you can calculate the phononic band gap, and then that can shift based on the periodicity that emerges from the different degrees of curvature in these beams. What we'll learn more is that we have quite a few degrees of freedom. We can induce rotation, bending, buckling, and expansion. And here's the best part. Once we understood how these defects affected things like band diagrams, we can tame them and we can program with them. And so here's one of these microlattices, and we now programmed a pattern into it. And watch what happens upon lithiation. You don't know what it is, but now that we're lithiating it, you can hopefully see the amazing resemblance between what we programmed and my little Caltech logo down at the bottom. So once we understood the defects, we can actually put them to use. And so this is a good point to finish, thank you for giving me the opportunity to share some of our recent research with you. And so if you walk out of here thinking, she showed all these videos and pictures and some things, and it's just a lot. So I'd like you to walk out of here with 3 key takeaways. If you're clever about your atomic level microstructure in the materials that you're interested in, the nano-induced size effect, how your material class responds to the reduction in size, and to the specific architecture that you're interested in, you can create entirely new classes of materials with not only unprecedented properties, but with unprecedented combinations of properties. And the reason why you would want to do that is so that our kids grow up in the world where there are no hearing aids, because we'll just be able to write the cochlea bone and insert it directly into your ear without any need for hearing aid, so that our iPhone 83 can hold its charge for a year without needing to be recharged every 24 hours or so. The balloons, of course, will be helium-free because helium is a precious resource and these things are stiff. So as soon as we figure out how to make them not be porous, we'll be able to evacuate the air, and vacuum is lighter than air. Christmas ornaments, of course, would never ever shatter again. And here's our perhaps our most exciting pursuit. So I saw there's some desserts, I think, some breakfast materials out there. So brownies, right? So what we're working on nowadays is chocolate nano-lattices, which are 100% taste, 99.9% air, and 0.01% calories. So with that, a huge thanks to you and to my group and to all the funding sources.
Thank you. Excellent talk. We have some time for questions. Please put your hand
now
up
I
to
can
call
see
for
everyone.
the microphone. I can't see, so yeah. Hopefully you guys can.
What? Perovskite? We haven't tried perovskites yet, but it's certainly something that a lot of the solar cell community, of course, is interested in. So that we would be delighted to learn more about that. We haven't tried it yet.
No, I have a couple of quick questions for you. What's your perspective on the gas storage property of these nanomaterials like metal organic frameworks, nanoporous silicon, or graphene? And can you explain why graphene is the strongest material we know, whereas graphite has the same type of layer bonding related to the sp2 hybridization? So why is graphene so strong as a material and graphite a lubricant?
Thank you. So, well, we're looking at 2 different phenomena, right? So when probing the strength of graphene, we're effectively stretching a 2-dimensional material. So what we're probing is the actual bond strength. And if the graphene is relatively defect-free, we should get to the theoretical strength, and that's why it's so high, right? But graphite is effectively a layered structure of these graphene sheets, so it's very susceptible to shear. And so it has no mechanism for resisting the deformation. So it's just 2 different phenomena.
Back here on the...
Hi. So considering the long-term sustainability of lithium cobalt batteries, could your same battery architecture be applied to something more like, an aluminum battery?
Yeah, so we are actually very interested in batteries and in sustainability in general. And so we're learning quite a bit. So sorry, am my understanding correctly, is your question, do the solid state architectures of the cathode lend themselves to different anodes? Or yeah. So that's exactly the point. That's the idea. The main reason for why the batteries right now, at least in my opinion, these days that there hasn't really been any major innovation in batteries is because of the electrolytes. The electrolytes are unstable, they're mainly liquid, you always need the binders, and they're unsafe and add a lot of junk and more. There are a lot of problems with the electrolytes. So what we're interested in is enabling a pathway how we can create all solid state batteries. And so the lithium cobalt oxide was the only way that we could, or create, using this approach to create LCO, was the only way to create the cathode, which can then be interdigitated into any anodes. In fact, we've tried it with carbon already, and or silicon, or you can use aluminum or anything else, or lithium metal. But it's the solid electrolyte that's really holding up. That's the roadblock right now. And so those of you who are working on solid electrolytes, please hurry up. Yeah.
Let's thank Professor
Oh,
Greer
all right.
for a fantastic talk. We're going to now take a break.